Here's an introductory lesson on stress-strain curves. I'm just going to look at a material as we stress it in tension, and obviously the resulting strain because of that, and we'll try to make a bit of meaning out of it. So before we do anything else, let's get a little piece of material. Don't know what it is. Let's just an imaginary piece of material. What we're going to do is clamp it on one side. Okay, so let's put a little thing there. Let's clamp that all on one side so it's not going to move here. And then we're going to apply a tensile force to that to stretch it. Okay, so as it undergoes strain, obviously it's going to elongate a little bit. Okay, but as we all probably know, conservation of material is not just going to elongate, but it's going to have to get a little bit narrower as it stretches. Okay, so the cross-sectional area there will decrease as it gets longer and longer and longer because of the load. Okay, so as that happens, the definition of stress is the force here divided by the cross-sectional area. Okay, if that's a little cylinder, pi r squared. As it gets longer, obviously the area gets smaller, so we would have to recalculate the stress each time. A smaller area, so therefore the actual stress, depending on that force there, it would be bigger than what it would appear to be right when it was at the start. What we normally do here is just ignore the change in cross-sectional area, and we just pretend it stayed the same. After all, when we start making a structure, it's the initial size of the thing which matters. So in a stress-strain curve, the stress is always the force over the initial cross-sectional area. So that's the apparent stress really, and in reality, any stress that we do calculate, the real stress, because the cross-sectional area is decreased, is actually obviously bigger than what it really is. Okay, so we're going to deal with apparent stress all the time instead of actual real stress. So let's just get this back to where it was. Okay, we started at 5 centimeters. Let's put a little mark there. So that's where we began. That's the unstrained section, the unstrained length. So just repeating, as we increase it, okay, there's a period there, okay, where I stretch it, and if I release that force, that tension, then it'll go back. Okay, so here we're in its elastic region. So I stretch it, let it go, it comes back. There actually is, for most materials there, a region there where that elastic part there, we have the stress is proportional to the strain in that bit. If that's the case, then we have Young's modulus, the definition of Young's modulus, where we have stress is proportional to strain. So stress equals Young's modulus times strain in one linear region. Okay, that's the linear region, part of the elastic region. If I go a little bit further, then that linear relationship breaks down, and I'm still possibly in the elastic region, but it's just not linear anymore. Okay, so I don't know, maybe that's the spot just there. And still, if I go a bit further, okay, and let go, it'll go all the way back to where it was. Okay, so still in the elastic region. So there's the linear region. The elastic region is a little bit further, not very noticeable normally. Then I get to a point there where I start having, I permanently change the shape of that material. I permanently stretch it. So if I go past this elastic limit, I'm now at the so-called yield point. The yield point's where it's now yielding. It's going to change its shape. It's given up trying to keep its original shape. So if I do that, okay, a little bit further, well, if I let it go, it's not going to come all the way back to where it was. Okay, so stretch it all the way up there, let it go, it comes all the way back. If I stretch it a little bit further, well, it's not going to go back to where it started. there's going to be some permanent strain there. Okay, so obviously it's going to recoil a little bit, but you see we have a little distance there where it's got a permanent strain. It's permanently elongated. If I keep going with that, okay, so the further I get, okay, release it again, it's going to come back, but it's not going to come back right to where it was. Okay, so I go further and further and further. This is a pretty stretchy piece of material, obviously. We get to another point, and look, I'm not going to draw this on the ruler, but we do get to another point, well, not necessarily a point, but a region, I suppose, where we've changed the shape of it so much that we're actually essentially lining up the molecules or the atoms inside that material, and quite often the intermolecular forces there, they're more organised, so the material starts getting stronger. So we enter this region called strain hardening. The apparent stress, you probably won't really notice it too much, but the real stress is going to get much stronger and stronger and stronger compared to its cross-sectional area, that is. And we will expect the strength of the material to increase. It'll be harder and harder to change. Finally, we get to a point, okay, I don't know, let's draw that up here, where I've increased my stress to some value there, where I've gone to the absolute limits of strain. Well, not the absolute limits of strain, but the absolute strength. So if I maintain that force there, maintain that stress, the material will just rapidly fail. We have a region there where we call it necking, where a section of the material is going to fails a bit earlier than the rest of it. Like obviously it's not uniform, and the material will start, necking out a little bit. Okay, so we have like a bone sort of structure there. So we have a region where it starts necking. The material starts losing its strength fairly rapidly, so less and less stress is required to keep it straining, and eventually it'll break. And as it breaks, obviously we've got a snap there. Okay, so that the graph will finish with a breaking point. Okay. Let's get rid of that. So what does that mean with all this? Okay, let's draw a graph. Let's get rid of that title. Okay, so if I had a graph, terrible line, I have stress against strain. Okay, let's use a different colour pen. There will be a region there, no stress, obviously no strain, but as I said, there's normally that linear region. Okay, so when I release it, okay, start stretching it, comes all the way back down, stretch it, comes back down in a linear relationship where stress is proportional to strain. After that, there's a not necessarily linear anymore, but let's just draw it like that. Okay, there's still in the elastic region. So if I stress it all the way up to that point and release it, comes all the way back down to where it was, no permanent strain. But I get to that point there where it's the yield point. Okay, so the yield point is just there, and depending on the material, sometimes it's a bit easier to strain it, give it a particular stress, and it might come back down. Who knows? Very easily stretched, easily strained, I should say. And then, as we said before, we get to some point where there's some region in there where we start changing the molecular structure. The intermolecular forces are more in line, so it makes the material stronger, and we undergo a region of strain hardening. Strain hardening. So let's use another colour. So strain hardening, as I said, the stress is takes more and more stress, so therefore it goes up to strain it a particular bit. I get to its maximum force that it can handle, its maximum stress. Okay, remember we said that was about that region there, where very quickly after that it starts necking and the material will break. So let's choose another colour, and then it's, as I said, it starts necking and then it's going to break. Okay, shouldn't really put that cross there, cross them along on the graph. Okay, so as it stretches, linear region, the whole elastic region, okay, not necessarily linear anymore, but we have the elastic limit, or the yield point. Then we have a section of just easy permanent straining. We go through a section of work hardening, strain hardening, and we reach its ultimate strength. Okay, the ultimate strength applies to some particular increase in length, particular stress. Undergoes a necking where it starts rapidly failing, and then the material breaks. So just one more thing there. What happens when we go from its elastic region into its plastic region? Okay, so this is the plastic region where it's got permanent strain. In it goes, as we said, when it comes back down. Okay, so remember we're down here, we went past its yield point, so we got some applied strain, if you like, release that, and there's some permanent strain behind there. Okay, so that's the amount of permanent strain. A very good approximation is that when we get to a particular point, okay, so we've gone past its yield point, it's going to have to come back a bit, so it recovers a little bit, but instead of following the curve back, it's going to come back down. Okay, so let's choose another colour. Let's see if the brown works. Okay, so let's say again we got to this point just here, and then as it releases, it comes back down, and we have some region of permanent strain. The approximation is that the slope of that line is equal to the initial slope of that linear section, and the slope of the linear section is obviously the rise over the run, which is stress over strain. So that region there is Young's modulus equals stress over strain. And this little section there, we have the same slope. So if you know the slope, you can come back down and work out its permanent strain.